Okay. Any questions? And then now we divide the sum of squares by their degrees of freedom, so which we usually call as the mean square. So the MSE, which we usually call S square as our notation, which is the SSE divided by n minus 2, follow the sigma square times the chi-square distribution with n minus 2 degrees of freedom divided by n minus 2. So we just divide n minus 2 here. And the beta of 0 is equal to 0 is true. So we have MSR is equal to SSR because we have one degrees of freedom. So MSR is equal to SSR. Basically MSR is equal to SSR divided by 1. That is sigma square with chi-square times chi-square distribution with degrees of freedom at 1 degrees of freedom. And MST is the SST divided by n minus 1, which is the follows the sigma square times chi-square distribution n minus 1 degrees of freedom with n minus 1. So, excuse me, if beta 1 equal to 0 is true, you can show that the MSR, expectation MSR and expectation of MST is equal to sigma square. Which means that if you look at this result, so beta 1 equal to 0 means that there is an expected value of SSR is equal to SST. Expected value of MSR equal to expected MST means that you don't, nothing is explained by this xi. So you don't have anything explained by this xi, this predictor, which is same as that your beta 1 is uh, is not informative in this variation. And then since we have this result, and then we can derive further result, and then we can use them for testing the beta 1 equal to 0. So we consider ratio of f is equal to MSR divided by MSC. And then under the beta 1 equal to 0, we expect the f to be about 1 because both the expectation of MSR equal to expected MSC equal to sigma square. And then if beta 1 equal to 0 is false, then we would expect that f to be greater than 1 because we have expectation MSR, which is equal to sigma square plus beta 1 square times sum of xi minus x bar square. If beta 1 is not equal to 0, then that is greater than the sigma square because beta 1 square is positive than xi minus x bar square, and the sum of them is also positive. And so it is reasonable to use this ratio as a statistic for testing H0, and then we will reject H0 if the statistic is significantly large. So if we have the reasonably large, then we can have the evidence that we can reject the H0. So under the beta 1 equal to 0, then the MSR divided by MSE is equal to SSR sigma squared divided by 1, and then SSC divided by sigma squared divided by n minus 2. And then, as you know, in the mathematical statistics, if so if you have the chi-square distribution with the degrees of freedom A and chi-square distribution with degrees of B, and they are independent, and the ratio that the chi-square random variable divided by its degrees of freedom has the F distribution with degrees of freedom A and B. So here, SSR is the under H0 is the beta 1 equal to 0. That is the divided by sigma square. It's the chi-square distribution with degrees of freedom 1. And then SST divided by sigma square is the chi-square distribution with degrees of freedom n minus 2, regardless of beta 0 equals 0 or not. So we have two chi-square distribution with dividing its degrees of freedom. The ratio, and then so it follows the F distribution with degrees of freedom 1 and n minus 2. So our this ratio MSR divided by MSC has the F distribution with degrees of freedom 1 and n minus 2 under beta 1 equals 0. So we can test this beta 0 equal to 1 using this F distribution as well as the T distribution. And then here in the simple linear regression, since we have one predictor, and then the one predictor can be thought as the our model, model because the if we remove this beta 1 in the model, then we just have the that is not the model with respect to this predictor. So here we are constantly model with the predictor. So this testing for beta 0 equal to 1, beta 1 equal to 0 is equivalent to the testing for this entire model. So we can create the ANOVA table here. So we have the regression and error and total, which is the source of the variation. So we have a sum of square, a sum of square due to regression, sum of square due to residual, due to error, sum of square for total, and its degrees freedom is 1, n minus 2, and n minus 1. And then we have the mean squares, so mean square of regression, mean square of error. And then we can calculate the F statistic, which is MSR divided by MSC. This is called this analysis of variance table, or by using the abbreviation, we call this ANOVA table. So this ANOVA table contains the very important information about the model. And then if you use the statistical software, then and then you run the linear regression by using the software, then you can see uh, this ANOVA table as output. And then we reject H0 if f is greater than f, and the f statistic with the 0.05. So as you know, we have this f statistic also the only has a positive value because of this ratio of chi-square statistic. So this is f, in our case, we're interested in critical value. F n minus n point of 5, which is this critical value is excuse me. So f, the probability that the f is greater than f1 n minus 2 0.05 is equal to 0.05, where f has the f determined with n 1 and n minus 2 degrees of freedom. So we can use the critical value from on the f distribution with the degrees of freedom 1 and n minus 2, or you can use the p-value. So if that is the less than 0.05, then we reject the H0. Any questions so far? So suppose that, so let me give an example. Suppose that we analyze the data with 5 observations about sales and environment advertisement. So we are looking at the effect of that, how the advertisement is associated with the sales. So in this case, the sales is our outcome and advertisement is our predictor. And then we have this information, 5 information. So yi square, sum of yi square equals 26, y bar is equal to 2, and the sum of xi I equal to 1 to n is equal to 15, and sum of the I equal to 1 to n xi square is 55, and beta 1 hat is 0.7. Then let's create the ANOVA table. So to create ANOVA table, we have to calculate this T input for the SSR and then the SSE. I mean, if you know, say, 2 of these 3, then you can easily calculate derive one of them because you have SST is equal to SSR plus SSE. So we have the information, sum of yi square and then y bar. You can easily calculate the SST. And then we have the sum of xi equals 15 and then xi squared is 55. And then we can easily calculate and also we have beta 1 hat squared, and we can easily calculate the SSR. So let's calculate this one. So SST is equal to sum of the yi minus y bar square, and then we know that sum of y square is equal to 26, and the sample size n is the 5, and y bar square is the y bar is equal to 2. So this is sum of y square, y minus y bar square is equal to sum of y square minus n times y bar square. So it's going to be 26 minus 5 times 2 square, which is 6. And then you can calculate the sum of the xi minus x bar square, which is also the sum of xi square minus n times x bar square. So 55 minus the 5 times the 15 divided by 5 square, which is the 10. And then you can calculate the SSR, which is beta 1 hat squared times sum of the xi minus x bar square, which is 0.7 squared times 10, with a 4.9. And then SST is equal to SST minus SSR. So 6 minus 4.99 is equal to 1.1. And then you can create the ANOVA table. So you can calculate 4.9 divided by 1 is the 4.9. Then 11.1.1 divided by 3, because we have a degrees of freedom for error is the 5 minus 2, which is equal to 3. So if you calculate this one, you can get the approximately 0.366. And then you can calculate the MSR divided by SE, which is 4.9 divided by 0.366, which is equal to 13.364. And also you can calculate the sum square for total, which is 6, and the degrees of freedom is 4, which is n minus 1 degrees of freedom, 5 minus 1, n minus 1 degrees of freedom. And then we use the critical value, which is the so f with degrees of freedom 1 and 3 is equal to 0.95 equal to 10.1. And since the f is equal to 13.364 is greater than 10.1, so we will reject H0 beta 1 equal to 0 at the 5% significance. This is how to create the ANOVA table. Any questions? Okay, so we have a next example, and I will give you 10 minutes, between 10 to 15 minutes. So please try to solve these two questions by yourself. Okay, let's get together. So we can first we can get the beta 0 hat by um, y bar, the 7.5 minus 0.5 times 9. Beta 1 hat times 9, which is the is x bar, which so it is 3. For the second item, so you can calculate that SST is the 11 minus 1 times the 4.13. So we have we have the this 4.13 is the variance of the sample variance of y times the 11 minus 1, which is the 10. So we can get the 41 by times 3. And the SSR is the zero point 0.5 square, which is beta 1 hat square times 110, which is the 10 times um, as, as sample variance of x, which is the 11. So which gives it 27.5. Then you can calculate SSE from the SST and SSR. So SSE is equal to SST minus the SSE, which is the 13.8. And then S squared is the 13.8 divided by 9, which is the 11 minus degrees of freedom. So S squared is 11 minus 2, which is 9, so which gives the 1.533. And then also we can calculate the square root of the S squared, which is S, 1.238. And then F, which is MSR divided by MSC. So MSR is equal to SSR, 27.5 divided by MSE, which is 1.533, gives it 17.9. So in summary, we have sum of square for regression is 27.5, sum of square for error is 13.8, and degrees of freedom for regression is 1, and the degrees of freedom for error is 9, and the mean square for the regression is 27.5, and mean square for error is 1.533, and then if you divide 27.5 divided by 1.533, you can get 70.9, and then you can um, calculate this critical value um, by using computer, which is the F critical value is 1 and 9 and 1.09 and 0.95, which is 5.117. Since the 7.9 is greater than 5.117, we reject the H0 beta 1 equals 0 at the 5% significance level. Okay. Any questions? Okay, so let's briefly talk about so I will give a brief introduction on the partial correlation. So um, until this time, we talked about Y and X for correlation and the regression, right? And then now we could think about one more variable, more variables, say Z. Z can be Z1 or Z2, and etc. It is very common that you have the more than one filter in your data set. So in that's the case, that we have some difficulty here. Now we only thought about effect of this one. So you have a say, x, y. You only think about this like in the regression sense, this direction, which means that we are looking at the association between x and y. So see, now you have the another variable. Let's say we have only one more variable, say z. Then it is possible that z is also have an effect on is associated with y. And then also they have correlated x and z maybe correlated, right? So x and z may be correlated. So now then the interest would be, so in correlation framework, what is correlation between x and y by controlling effect of z? So that can be our main question on here. Or you can think about the if you have more than one variable, then what is the effect of the like what is the correlation between x and y controlling effect of the um, say g1 and g2 or gk if you have a other k other predictors. Like so if you have suppose that you want to find association between uh, GPA and study time, or let's say this. Um, then you may have many other factors may and then you may have many other factors that may be associated with blood and pressure and the diet. For example, you can think about age, and their race, um, and their socio-economic status. For example, age and race and their socio-economic status may be uh, correlated with the blood pressure and diet. Does it make sense? then our interest is the finding association between blood pressure and diet controlling effect of the age and race and other possible factors. So that's the concept of partial correlation. So in the next time we are going to talk about the partial correlation, and then from there, then we are going to talk about the multiple linear regression, which is the case when we have more than one predictor. Okay. Okay. So homework 2 is posted. That's due on next Monday, 28th, on 1:30 p.m. And then I will give some information about the exam in the next class.
Dr. Cho,
Yes?
just to make sure for the homework, the first problem and the last one are done with R, right? And the number two,
Yes.
number
For
three,
the
it's by hand.
computation problem, it should be done in R. So
Thank you.
any other questions? Okay. So I will see you in the Wednesday.